You're responsible for nodal analysis, which is my favorite. It's easy. And now you don't need to write this down. It's obvious. Mesh, right? Nodal and mesh are the two big ones. Then you got Thevenin's analysis, which is great to reduce a circuit to two elements, a source and a resistance, and you can put any load you want on, right? Then after that, there were source transforms, both Thevenin and Norton source transforms. Then there was superposition, right? Superposition usually takes the longest, in my opinion, but it gets the answer done. It'll get the answer. So those methods you're responsible for, and you will be tested on them pretty thoroughly. Now, today we're going to move into transient analysis. This is in the book that you bought. It's all over the internet, and it's going to be things you're relatively familiar with. I'm going to start with capacitors and resistors. You're familiar with the term capacitor from physics and inductor from physics. But I'm going to go through the equations that govern them in the time domain, and the analysis we're going to be doing is transient analysis. Before I start, I have to tell you this. We write a differential equation and solve it, but we are not going to use Laplace transforms or integrating factors. I'm going to show you the two general forms of the solution for these equations and how to get it. Do you understand that? So I'm not expecting you to know Laplace transforms. If you see Laplace transforms in your book, that's great. If you want to use them, have it, knock yourself out, but you don't need them. All right? With that in mind, and there's this generally, I let you pick the date, and I pick the date about midway through this chapter, or through the transient analysis. That's generally what I do. If you want to do a date, now this is up to you. What I'll do, if you want to schedule a test, look at your schedule, and then on Monday, if somebody can remind me, like the entire front row, remind me, and I'll just do this. We'll put up three possible dates, and then a show of hands vote. We'll take the top two and vote on it, all right? I try to do this as fair as possible. This is a huge class. You've got a diverse background. I don't know who has tests when. Somebody's going to be unhappy. I'll give you one piece of advice. Monday tests, in general, are the highest average. Fridays, in general, are the lowest average. I've been at this a long time. I've had large and small classes. It never fails. The reason Monday test is pretty obvious. You have the weekend to study. Good students study hard. Poor students don't. So you get the biggest discrepancy in grades on Monday. Friday, you're fried out. You got all sorts of things to do. Those are the worst scores, on average. Just telling you the way I see it from my perspective. It may not be true for you. There's always exceptions, but that is how it's true in general. If you're a serious student, a Monday test is the ideal, usually. All right. Now that I did that, now transient analysis. This is important. You've had a lot of this before. Some of you will just glide through this. You won't even blink because you know it. Others are going to struggle. If you're strong in physics, you'll probably do very well in this. So for starters, we identify a new component that you're familiar with. This is a symbol for what's called a capacitor. A capacitor, first of all, the symbol is C, and the units of capacitance are farads, all right, or just capital F. How many have seen the term capacitance before? If you don't have, put your hand up. Either you're too tired or you haven't had physics and you don't belong. It's one of the most common things in the world. Capacitance. Now, what is a capacitor? Fundamentally, it's two pieces of conductor. They don't have to be parallel. And it's separated by something called a dielectric or an insulator. So no DC current can move from one plate to the next through the actual insulation. You follow me on that, class? That's a capacitor. The thing that governs capacitors' voltage-current relationship is this. Please write this down. If you have a current I of T entering a terminal, you will label this, let me get this out of here for a second. You'll label the terminal that the actual current is entering as plus, the terminal the current is leaving as negative. Now again, I'm defining that as the direction of current means that I'm assuming it's going that way. And if such, the voltage that would be developed V of T here would be equal to C times the derivative, the current, my bad. The current, if this is a voltage here, V of T, and a current I of T would be equal to C, the value of the capacitance, times the time derivative with respect to T of the voltage across that capacitor. It's I equals C dV dt. Follow me on that, everyone? Now, one thing you'll notice, if the voltage across the capacitor doesn't vary, a DC voltage, there is no current. And current is flowing in that direction. So literally, think of it as flowing right through there, even though real charge doesn't move. It's called a displacement current, where charge on this plate will displace charge on this plate and cause a current. Do you follow me in this class? Now, how do we go about solving circuits problems? For starters, we do this. We say if we have a capacitor here and a resistor here, right, and we have a voltage across these two, you all agree they're in parallel, right? Agree, class? If we look at that for a moment, I know if they're in parallel, the current here, if this is R, I and the resistor of T will just be equal to V of T divided by R. You all agree with that? Now the current this way in the capacitor, call this, I'll put it outside, I C of T. Well, I C of T will just be equal to C times the time rate of change of that voltage. Does everybody agree with that? Now some people say, well, how did that voltage get there? That doesn't matter. If there is a voltage there, for whatever reason, the current this way will be equal to C dV dt, and the current this way will be equal to V of T over R. Does that make sense to everybody? Now one thing you'll notice, if I do this as standalone, so there's nothing coming in here, right? It means the sum total of this current plus that current would be 0, wouldn't it, class? How many see that? If nothing's coming in, what's going out has to add up to 0, right? So that means that if I have C times dV, and I'll put a sub C here of T dt, plus VC of T divided by R, that's equal to 0. That's called a homogeneous differential equation because it's not equal to something else. It's equal to 0. Now to solve this, you know, I really hate to spend much time on this because you're engineers and you can do this blindfolded probably. You divide by C for starters. Do you all agree with me? Now I got the derivative, the highest power derivative with a coefficient of 1. Then what I do is set this equal to that. So I say, I'm not using Laplace transforms. I know you guys are just wishing I would. In electrical engineering, you do. In mechanical, you probably do. In aero, you do. But there's probably some people that don't use Laplace transforms that much. I mean, that's sort of my world I live in. Now, when I get this, the way I solve it, multiply both sides by dt and divide by dc of t. All right? Now, what is 1 over x dx integrated? Natural log of x, right? This is like the differential of v over v integrated is natural log. Do you follow me in this class? I did it this way on purpose to make it easier to see. So this becomes the natural log of vc of t is equal to minus dt, really. The integral of dt is t, so it's really t over rc. But because this is an indefinite integral, you have to add a constant. I'll call that k1. Is everybody with me on that? Right? There's no trick. It's the simplest thing. It's high school to most of you. All right, now, after that, the only thing I do is I want to solve for VC of t. So I have log of x equal a constant. To find out what x is, take everything to e to that power, right? So then I get VC of t is going to be equal to e to the minus t over rc, right? And it's plus k in the exponent. Do y'all agree with me here? I'm going through this simply and slowly. I'm not doing anything crazy. I don't know if he uses Laplace transform, it's in his book or not. So I'm just telling you, I don't know what he uses, but you don't need it for this. Yes, sir?
You just go through what? You want comfortable.
K1 is just an arbitrary constant. When you do an integration of an indefinite integral, you have to add a constant, right? If this had limits A to B, you would. Where's the C1? If you want to put a C1 there, I don't use C because C is capacitance. That's the reason I don't. All right. You follow me on this? Yes, sir.
Can you explain again why the sum of the functions of the two currents is equal to 0?
Because there's nothing going in. Remember Kirchhoff's law. All the current going in is equal to all the current going
So
out.
we're studying it with no current flowing in?
For now.
Okay.
And the reason is I'm taking the simplest possible example.
Okay.
The more complicated it gets, the more people get lost.
Thank you.
And I'm not doing Laplace transforms. I'm not going to use crazy integrating factors. I'm going to keep it simple. Now, when I get down to this point, right here, I can break this out and just say this is really equal to VC of t is equal to e to the minus t over RC times e to the k. Do y'all agree with that? Just break it out. E to the AB is e to the A, e to the B, right? Well, e to the k, isn't that another constant? So, I use K1. I'm just going to call this thing, I'm just going to call it V naught as my constant. And that's VC of t. Now that's the general formula for voltage on a capacitor with only a resistor in parallel and nothing else added. Do you understand that? And what do you see there? That's exponential decay. At t equals 0, if there was a voltage V naught, it would exponentially decay to 0, correct, class? And how many remember this from physics? Or high school physics, or whatever you had in electronics? This is probably, this is the equation I had, I think I was a sophomore in high school. So this is stuff that we've all seen many, many times in many, many different ways, right? Now, here's the difference. And whoever asked that question about the currents, it's a good one. The difference would be if there were, I'm going to say other factors for now, and I'll get to this other thing. If, for instance, there's a force, voltage, or current in here, constant current, something like that. All right? Now, here's the way that it changes, and what I'm not going to do is write the general equation solver, because that would require Laplace transforms. So what I'm going to do is say, if you got a capacitor in the circuit, in general, no matter what, this is the equation that will solve it. If it's a transient problem where the voltages are either on or off, and I'll show you what I mean by that, but write this equation down. In general, your solution for the voltage across the capacitor will be equal to sum K1 e to the minus t over, and then put R Thevenin here times C. I'll get to that. It's the Thevenin equivalent resistance across the capacitor, and you'll see what it means, plus K2. I'll give you circuits and do problems in a second. This is the general equation for the voltage across the capacitor. We will solve for K1 and K2 in a second for specific problems. Yeah.
Is the C in the...
This is a capacitance value.
Is that in the denominator with respect to T?
Yeah. This is a constant. In general, they call R Thevenin times C tau, but I don't want to do that yet. What I'm trying to do is make this as easy to understand as possible. Now, what I'm going to do is show you the steps that you use to solve this for transient circuits. But what I'm going to do is put up a general form of a very simple circuit, a little bit more complicated than the first one, that will allow you to see how this is done, all right? Now, please record this and be very careful to write this down. All right, now, if you have a capacitor, I'm going to just show you a capacitor. I'm going to say I have a switch here. This is a symbol for a switch. When you put t equals 0 or any time there, it means it closes at t equals 0. Follow me, class? I think in ME you have similar symbols. I don't remember what the symbols are, but in electrical engineering, this is a switch, and it means it indicates the time the switch closes. It's open until it's closed. The other thing is, if it's closed and it says t equals 0 and the arrow's going the other way, it means it opens at t equals 0. Follow me on that? It's standard. Then what I'm going to do is put a resistance right here. I'm just going to call that R1. And I'm going to put a voltage here. I'm using the symbol for a battery. So I'm going to put this as, say, V0. That's R1. Then over here, I'm going to have a capacitor and another resistor. Now what I'm going to do is find out what the output voltage is. Now I want you to take and listen carefully. The voltage that we always solve for, regardless of what's asked for in the problem, is the voltage across the capacitor. For this problem, it has to be the same. What you're after is this voltage. It happens to be the same as V out. If they were worried about the current through that, if that was the output they wanted, we'd still start by solving the voltage here. Understand, everybody? It is the voltage across the capacitor we always solve for these transient problems. The reason they're called transients is when that switch closes, all of a sudden, the output becomes transient in nature. It'll have a shift, either up or down the voltage you go, and then it will asymptotically approach a constant value as t goes to infinity. Do y'all follow me on this? Now, the equation that governs this voltage, Vc of t, is equal to some k1 e to the minus t over r Thevenin times c plus k2. Listen carefully. The order of these steps is not really important. But what you always do in general, the best way to do this, is start by saying, what is Vc for t less than 0? Less than or equal to 0. Really where the switch closed. If it's the switch closed at 1 second, find the voltage for t less than 1 second. Follow me, everyone? All right, what is that? Well, if you look at this problem, and there's no stated voltage here, it's 0. How many see that? If you just hook this thing up and that switch is open, that's 0. Do you all see that? So you put a 0 there. Not 0. What? What? I'm sorry? What are you? Oh, you were trying to picture.
No, I took a picture of the.
You can take a picture. Can you all see this recording okay?
Yeah.
I mean, the video, I looked at it, it looks good, from what I can tell.
Yeah, good.
How many of you have seen it, just out of curiosity? Now, it's using GroupMe, is that right? I've never heard of that before. All right, I just keep on getting messages on my phone, so I shut the thing off. Anybody else have that problem, or is it just? It drove me nuts the other night. I want to hear that you drove me nuts. All right, now, I wish there was a way you could stop that.
You can.
Anyway, so that's it. Now, why did I say that? Because now I can go up here and say that Vc at t equals 0 is 0, right? You all see that that means this is 0, right? Is equal to what? Well, it's e to the 0. What is e to the 0? 1, right? So it's just k1 plus k2. Ah, great. You got one equation with two unknowns. This is like differential equations back in the day. You did what? You get the general form, and then you use the boundary conditions to solve for the constants. Remember that? So now we find the other constant, really, we find two equations. Now we find the voltage at Vc as t goes to infinity. And here, I have to tell you something. I want the voltage across the capacitor as time goes to infinity. Please listen. Remember the equation for current through a capacitor. In general, you had plus to minus V of t, Vc of t, you had a current I of t going in, and the relationship there was Ic of t is equal to C times dVc of t dt, right? I'm stating it explicitly for a reason. That's a DC voltage. Once the switch is closed, the transient mode starts. But as time goes to infinity, for a first order differential equation set to a constant, it's got to go to a constant solution for voltage. How many understand that? How many believe it? You throw the switch, the voltage out here, after enough time goes by, will stable out. It'll be a constant. Follow me? Now, another thing I'm going to tell you, that the capacitor looks like an open circuit to DC voltages. Did you hear me? A capacitor will charge to the value of the voltage. I mean, it's really, the charge will be equal to Q, or Q will be equal to charge, the charge will be equal to C times V. Whatever the voltage is times the capacitance will be the charge on the plates. However, what happens is this. This thing fundamentally looks like an open circuit at t equal infinity. Can you all see that? Now, for t greater than 0, what happens is this. This is for t greater than 0. It looks like this. Do you all see that, class? The switch closes. For t greater than 0, that's what it is. When t goes to infinity, you might as well just disconnect that capacitor. Do y'all understand that? It looks like an open circuit. And what you're after is this voltage. You're after the plus to minus VC as t goes to infinity. Now, how would I get that voltage? Anybody? Most people don't want to talk in class this size. They're shy. But I know you're not shy. How do you get it?
Oh, please don't do this.
That's even better. I'm not shy. I don't want to talk to you.
Like solving for beta.
Yeah, kind of. But isn't this voltage division? Don't I have one resistor in series with another resistor with one source, right? And isn't the voltage across this resistor the voltage here, class? How many see this? I'm not trying to be a pain about this. I'm just trying to make sure you all see it. Do you all see it? It's gotta be, right? Well, what is that voltage? Isn't it just whatever the battery voltage is, V naught, right? And then it's voltage division. Then it's simply R2 over R2 plus R1. Do you all agree? Everybody? How many see this? All right, we're missing a heck of a lot of people. I guess that no quiz meant party time. Because I haven't seen that many people missing from here in a while. Unless they all drop.
That's also possible.
Make them I've never done that. I'm thinking, fun game to play. They're going to hate you for that. Yes? This is R2. This is R1, right? Aren't these two in series?
Yes.
Isn't the voltage across that resistor the voltage across that capacitor? So I just want the voltage across the resistor as t goes to infinity. That capacitor looks like an open circuit. Follow me?
Okay, so what does that say right there?
That's V naught.
Yeah.
That's V naught. Source voltage. Let me, it's times R2 over R2 plus R1. That's all it says. Can you all read my writing back, you guys? Far back?
It's kind of hard.
Here. There. Can't read that, move up front. Yes?
So the reason we're treating it like an open circuit is because the capacitor is full.
Look over here for a second. Do you agree there's no change in the voltage across the capacitor as t goes to infinity?
Yes.
All right, how much current's flowing in that capacitor? What's the value of this derivative as t goes to infinity?
0.
What's the value of current?
0.
If current can't flow, it's an open circuit. That's it. Got it? Yes. Are you asking a question?
Yeah.
Give me 1 second what you said.
Yeah, I was wondering if the capacitors is like a water, if it's like a water and
A what?
if it's like a bottle, like that's.
How about we talk about that after? All right. Yes, sir.
So with the,
Speak up, guys.
voltage or charge goes from the battery to charge your capacitor, does that mean that the voltage will change or be not constant?
V naught is a constant. It's like a battery. Think of it car battery. Right? If that, yeah, you can, turn things on. The voltage is still like 12. All right? Great. I'm not going to write that big. If you can't see, move up. And I'll do my best. However, I do understand. This is going to be V naught here times R2 over R2 plus R1. And I do appreciate the fact that you had physics, thank God. So this is just rehashing stuff. I mean, you did have physics. Come on, give me a break. No one did that. Oh, we never heard of it. All right, got me on this, guys? Now, The next thing we need, listen carefully, we're almost there. With these two equations, right? Look, if that is this, say this is VC, I'll just call this VC of infinity here. You all see that, what is the voltage as, what does that happen, what happens to this equation when time goes to infinity? You see that that's equal to what? Just K2, isn't it? K1 is 0 because e to the minus infinity is 0, isn't it? How many see that? So the voltage at infinity across that capacitor is K2. Y'all, hey, Sumin, come here for a second. Y'all agree with that, everyone? Now, the last thing, come on down. No, I need you to come down. You're going to do me a favor. You're going to go up and get some. I thought I had to give a quiz in the last class. I didn't have time to run up to my office. Sumin, it's on the desk. So good. It's in my office. Thank you. Here, when you look at this, the next thing you need, we're almost there. Do you agree that this right here is just K2? We can find K1. Agree? But there's one thing we've got to get. That's R Thevenin. Now listen carefully. The way you find R Thevenin, so now we're going to find R Thevenin. You look at the circuit for t greater than 0. Not for t less than 0. It's after the switch does its thing. Follow me? And then you take a look and find a Thevenin equivalent resistance right there. So now you want to find R Thevenin right here. Now how do you find R Thevenin? I'm going to stop. Listen carefully. Well, Thevenin voltages, you know how to get. Thevenin resistance is always you turn off the sources, right? And you see what the resistance is across these two dangling leads where the capacitor was. Got me on that? So when I turn off the voltage, what does this become, people? Just a wire, short circuit, right? Now, take a look. How many see they're in parallel? Take a good look. Y'all see it in the back? All right. I appreciate your attention to this. And I know some of you think I'm being silly, being this slow and stuff, but it's necessary because some people really don't know this, all right? Most people have had this in physics. You've gone through the equations, you know this, but some people don't. So now R Thevenin here would just be what? R2 R1 over R2 plus R1. Do you agree with me? Now you can solve because you've got K2, therefore you can solve for K1, right? And you'll notice K1 is what?
Negative K2.
Minus K2, agreed? Y'all see that, everyone? Then you can write the general equation, and I'll put it right here. You can say VC of t is equal to K1, right here, which is minus K2, which is this, so it's minus V naught times quantity R2 over R1 plus R2. Well, actually, let me do it this way. It's equal to K1, I'm just going to use this V infinity here, K1 e to the minus t over tau, and I'm going to say tau is equal to R Thevenin times C plus K2. Now, I know K2 is this, so I can replace that with just VC at infinity, at t equal infinity. And I know K1 is minus that, right? Correct, class? So I can write this. I can say VC at infinity times 1 minus e to the minus t over tau. And that tau is right here. You all see this? Now I want you to take a look at this. Please listen to me. How many see this right here? I'm just manipulating, and if I put numbers in, it'll be a little clearer. Now when you look at this for a second, what does it really look like? Well, the voltage at t equals 0 is what? Take a look. Well, what's e to the 0?
1.
What is 1 minus 1?
0.
Therefore, 0. Yeah, the voltage is 0. But what's it doing? It's climbing at an exponential rate, a decaying exponential rate to a value of just the voltage at infinity, right? So if I was to plot that voltage on the capacitor as a function of time versus time, and this would be 0, what I'd see it do is this, where it's asymptotically going to approach VC at infinity. And that's a very common type of behavior for first order circuits, transient circuits. They're asymptotically approaching a constant. You see it a lot in first order differential equations that govern things. Now, second order are a little different. MEs run into second order and third order, but you know, the PV equals nRT type stuff. You can write that as a time varying form, Boyle's law, but it doesn't, well, you can't actually do it that way, but there's a differential form for some of these things in mechanical engineering, like diffusion equations and stuff like this. They'll give you the same basic form as I'm showing you here. So try to understand. Okay, next, after that, we're going to take a short break and I'm going to hand this back.
What is that value, next to DCTs, right?
Right here?
Next to it.
That's asymptotically the value of infinity.
Okay.
It's just the voltage that's going to go there. I'm going to give you some real problems. Tell you what, Suzanne. For this problem, you got a 12 volt DC source. Then you have 3K in front of it. Now listen to this. That switch is closed for t less than 0. You all see that? It's closed, it's on. It opens up at t equals 0. You all see this, class? Now, it's got a capacitor here, and it has 2 resistors here and here. You all see it? Now, what would be asked for in the problem statement would be this voltage. But you don't get that voltage. You get the voltage across the capacitor first. You follow me on what I'm saying? You can get that voltage in a second after you get this voltage. So, the voltage across the capacitor, the general form is this. VC, I'm trying to get a marker here if it works. VC of t is equal to some k1 e to the minus t over, I'm going to put it R Thevenin times C, right, plus k2. Now, the steps I gave you really don't matter in the order, but I'm going to go ahead and do in the order I've showed you, right? First, you find the voltage at t equals 0. So the first step, VC at t less than or equal to 0, because that's where the switch changes. I want you to watch this carefully. Now, for t less than 0, that switch has been closed forever. You'll follow me on that. It has been closed since time began. What does the capacitor look like in that domain? T less than 0. Class? Open circuit, because there's nothing changing. You follow me? So the voltage across this capacitor is really the voltage across these 2 resistors. Does everybody see that? Did you get most of them? All right, thank you very much. I appreciate it. Class, if you didn't get your quiz, come on down. They're up there somewhere. And I do mean it, I thank you. I'm trying to focus on this. All right, now listen to me carefully. You all see that again, that the capacitor looks like an open circuit for t less than 0 because that switch has been closed forever. It opens at t equals 0. Do you agree with that? So what's the voltage across that capacitor for t equals 0? What is the circuit really, no it ain't 0. What does it really look like? Well, if we replace this by an open circuit, what does it look like? We have 12 volts, right? Then we have 3K, right? And then we have, and this is where that used to be, right? This is plus to minus VC, but it's for t less than 0. Then, can I put the 4K and 2K in series? How many see that? Honestly, do y'all know? Does anybody not see it? These 2 are in series, are they not? I can replace that with 6K. So what is the voltage right here going to be? Anyone? How many realize this voltage is the same voltage across that 6K? Show of hands. Well, what's the voltage across the 6K? It's gonna be, all right, you're using voltage division, you'd say, you're right. V6K is VC for T less than 0, and it's equal to source voltage 12 times resistance 6K over 6K plus 3K or 9K, right? Right? So that's 2/3 of 12 or 8. Is it not, class? That's 8 volts. All right, so that's 8 volts. And that's equal to K1 plus K2, right? So now we've got one equation. Now yeah. Your question.
Should that be T less than or equal to 0 or just less than 0?
All right. We're engineers. If you can find 0, you're better than me. T less than or equal to 0. Mathematicians would throw tomatoes at me if I did that. I'm not writing articles in some abstract math magazine. I'm solving problems. Back to this. You're right, though, just for the record. If back to this problem, now I need to find the voltage as t equal to infinity, right? So what's the voltage as t goes to infinity? I heard it was a 19-point spread in our game. We're favored by that. I don't know if it's true. My other class told me. I hope it's right, but I'm scared. Whenever I see that kind of spread, it's like, uh-oh. People relax, everything fails. What is the voltage at t equal to infinity? Now what happens to the switch at t equals 0? Yeah, I'm going to make a point here. So this is for t greater than 0. This opens, right? This part of the circuit is disconnected from that part, right? Now here's the truth. If there are no voltage or current sources in the circuit where the capacitor exists, after the switch changes, then necessarily the voltage will decay to 0. Did you hear me? Necessarily the voltage will go to 0 because current can flow and there's nothing to support this voltage. It'll decay to 0. How many understand that? All right, so this is 0, which is nice. Right, and what is that? Well, that's just K2, isn't it? Voltage as t goes to infinity is K2, correct, class? And that means that K1 is just, since that's 0, K1 is 8. Do you all see that? How many see this, class? Y'all with me? If K2 is 0, K1's got to be 8, right? Now, I got to get R Thevenin too. Remember, R Thevenin for the across the capacitor in the region after the switch does its thing, opens or closes, right? So what is R Thevenin? Think about R Thevenin as t goes to infinity. What would it be? Well, R Thevenin, how do I get it? I erase the capacitor. Don't have to erase the capacitor. But in a certain length of time, you're not going to worry about that capacitor. You'll see through this. But what's the Thevenin resistance across that? Anybody? There's only one resistance, really. Well, actually, in that circuit, there's two. But what is it? How many see it's 6K? It's just a series combination of those two. How many see that, people? Can you all in the back see that? I am always worried about people in the back. Because when I sit back there for Senate meetings, when I used to, some of the stuff out here, I could, what are they talking? It's hard for me back there. But y'all see it, though? All right. Now, we got R Thevenin and 6K. So what is our final equation? VC of t is equal to 8, right, times E. I didn't put a value for C in there, did I? For this one, C is 100 microfarad. I'll draw it back here. And this actually was and this is the voltage we have. 8e to the minus t, and that's R Thevenin times C, right? Now, normally they put that as tau. So this is going to be for t greater than or equal to 0. Tau is equal to R Thevenin times C. That was going to be equal to 6K times 100 microfarad. The units would be time. If you look at this, that's 6e to the third, and that's really going to be 1e to the minus 4. Oh, sorry. or it's equal to 0.6. Do y'all see that, class? It's 0.6, it's R Thevenin times C. C was 100 microfarads, that's 100 times 10 to the minus 6, or 10 times 10 to the minus 5, or 1 times 10 to the minus 4. You follow me, everyone? So that's 0.6. That means this equation would actually be 0.6, and this would be the equation for VC for t greater than or equal to 0. Does everybody follow me on this one? This is a straightforward method. Yes, sir.
So why does K1 disappear again when?
What's the voltage as t goes to infinity?
Is 0?
Has to be, right? This is disconnected, isn't it?
Yeah.
That's the reason why.
Okay.
And there are no dumb questions. You're going to be asking things that all of a sudden you slap yourself. What did I ask that? Ask it anyway. All right. There's other people that are wondering. Yes.
So we do R7 based on the system after 0?
After the switch transitions. If it transitions at 1 second, look at it at 2. Think of a t equals infinity. Find that value. All right. You can't go wrong there. All right, class. All right. I'm going to do some more of these. These problems. When you get the hang of the trivia, you can laugh.
What are the units? Units of resistance and
Hold, come on, guys, give me a second. R times C will have seconds as a unit. All right, now I can prove that to you later. But